In this lecture, we are going to study permutations and their cycles. So let U be a finite set. Then a permutation of U, or the collection of all permutations of U, is denoted by perm square brackets U, and it is the class of all functions sigma from U to U, such that sigma is a bijection. All bijections from U to U are called permutations of U. Intuitively, you can think of them as ways of taking the elements of U and shuffling them around. For example, if you take a deck of cards and shuffle it, then you get the cards in a new order, and that's a permutation of the original deck of cards. A permutation is visually represented by a directed graph. So corresponding to the permutation sigma, I will associate a directed graph called gamma subscript sigma. So what are the vertices of this graph? Just the elements of U. And what are the edges? So these are directed edges. You have a directed edge from U to V if sigma of U is equal to V. Now, if you take any vertex U in this graph, then there's a unique out edge because sigma is a bijection, and so there's a unique edge going out of U which must join U to sigma U, and there's a unique in edge because U is again in the image of a unique element of sigma, a unique element of U, and that is we can write that as sigma inverse of U. So every node has a unique in edge and a unique out edge. Of course, it's quite possible that sigma of U is equal to U, in which case this edge is a loop, so with loops, and this is of course equivalent to sigma inverse of U is equal to U. So it's a graph where every vertex, where loops are permitted, and every vertex has a unique out edge and a unique in edge. A consequence of this is that every connected component of gamma sigma is a cycle, a directed cycle. What I mean is that you have a sequence of nodes U1, U2, U3 all the way up to UK minus 1 UK, where U1 goes to U2, U2 goes to U3, U3 goes to, and so on, and UK goes back to 1. And we denote this, we call this a K cycle, or a cycle of length K. Okay, and K can be any integer greater than or equal to 1. In particular, if K is equal to 1, then you just have an element U which goes to itself. This is a 1 cycle. A 2 cycle is you have two elements U and V, U goes to V, V goes to U, and so on. And we usually denote this by saying U1 UK. This is a K cycle. We say that this is a K cycle. Now, the choice of where to start enumerating U1, U2, UK is quite arbitrary. This K cycle is the same as the K cycle U2, U3, UK, U1. Okay, and there are K such equivalent representations. You can also start with U3, U4, and so on, and end with U2, etc. Now we are ready to define the cycle structure of a permutation. It's just an integer partition of the cardinality of U. It's just the lengths of the cycles of sigma written in weakly decreasing order. So that means that this is integer partition of the cardinality of U. For example, let's look at a case where U has 5 elements, U1, U2, U3, U4, U5, and say U1 goes to U3, U3 goes to U5, U4, U4 goes to U1, U5 goes to U2, and U2 goes to U5. Then here, the lengths of the cycles are 3 and 2. We write them in decreasing order and we get this integer partition of 5. So if this is sigma, then this is the cycle decomposition of sigma. An important feature of permutations is that using a bijection from one set to another, it's possible to transfer permutations of one set to permutations of the other set. This feature will become very important. In fact, it will play a central role in the combinatorial, in the theory of combinatorial species. So let me take this opportunity to introduce it right here. So suppose you have two finite sets and you have a bijection f from U to V. And suppose you have sigma, a permutation of U. Then it's possible to transfer sigma to V. I'll call it f sigma. So it's the transfer of sigma from U to V using f. And what this f sigma does is it takes fu to fv. So f sigma fu is equal to fv if and only if sigma u is equal to. So if sigma takes u to v, then we ask f sigma to take fu to fv. And this gives rise to a well-defined permutation on V. And this is called the transfer of structure. Let me just so we have this permutation here on the set U. And suppose we have another set V and f takes U1 to V1, U2 to V2, U3 to V3, U4 to V4, and U5 to V5. Then you can just draw the same arrows between the V's as the U's. So f takes, let's say, f takes this to this, this to this, this to this, this to this, and this to this. Then I can just define f sigma as, well, it'll be the same picture. V1 goes to V3, V3 goes to V4, V4 goes to V1, V5 goes to V2, and V2 goes to V5. So I've transferred the permutation structure from the set U to the set V. And what is obvious from this construction is that U1 UK is a cycle of sigma if and only if FU1 FUK is a cycle of f sigma. In particular, what we have is the cycle type of sigma is equal to the cycle type of f sigma. So what we're saying is that this map sigma goes to f sigma is a bijection from perm U to perm V that preserves cycle time. So in particular, what this says is that if we study permutations of one finite set U, we are in some sense also studying permutations of any finite set V which has in bijection with U. So for each cardinality, we only need to take one set of size n. So in particular, let's take the set U to be our favorite set of size n, namely the set of integers from 1 to n. Now in this special case, perm U is just denoted by Sn. This is really what I mean here is perm of box n, but that's sort of clunky, so I've abbreviated it to perm n. And this is called the symmetric group. We'll talk about why it's a group a little later, but that's perm n. And for any set of cardinality n, you have a bijection from any set U of cardinality n, you have a bijection from perm U to perm n, which preserves the cycle structure. Let's just look at an example where n is 3. So if n is 3, there are 6 bijections from the set 1, 2, 3 to the set 1, 2, 3. This here is the directed graph visualization of the identity permutation. 1 goes to 1, 2 goes to 2, 3 goes to 3. So its cycle type is 1, 1, 1, and it has 3 cycles. Here we have permutations which have 1, 2 cycle and 1, 1 cycle. There are 3 of them. So this first one here, this takes 3 to 3 but interchanges 1 and 2. This one takes 2 to 2, interchanges 1 and 3. This one takes 1 to 1 and interchanges 2 and 3. So these 3 have cycle type 2, 1, and the total number of cycles here is 2. And finally, we have the permutations which consist of a single 3 cycle. So there are just 2 of them. 1 goes to 2, 2 goes to 3, 3 goes to 1, and the reverse, 1 goes to 3, 3 goes to 2, 2 goes to 1. So these have cycle type 3, and the number of cycles is 1. So we can try to count the number of permutations with a given number of cycles. And that's called the Stirling number of the unsigned Stirling number of the first kind. It is denoted by sigma nk. So here we'll assume that n is a non-negative integer, 0 less than or equal to k less than or equal to n. Actually, you can take k also to be any non-negative integer. So I'll just say n k in the set of non-negative integers, and sigma nk is defined to be the number of permutations. Maybe I should just not call it sigma. Let's call it little s nk is defined to be the number of permutations sigma in Sn such that sigma has k cycles. So let's just use the notation. So here in this, from this table, we see that of course you cannot have a permutation with 0 cycles at all unless n itself is 0. Every permutation has at least 1 cycle. So sigma 3 0 is 0. Sigma 3 1, well, there are only 2 permutations with 1 cycle. So sigma 3 1 is 2. Sigma 3 2 is 3. the 3 permutations with 2 cycles, 3 permutations in S3 with 2 cycles, and there's 1 permutation in S3 with 3 cycles. So these are the unsigned Stirling numbers of the first kind. This unsigned needs to be specified here because conventionally Stirling numbers of the first kind come with a sign, but we'll come to that sign a little later. So here we're just looking at the unsigned Stirling numbers of the first kind. And here's a claim. How do we compute them? So we can use a recurrence. For the unsigned Stirling numbers of the first kind, I claim that Snk is equal to Sn minus 1 k minus 1 plus n minus 1 times n minus 1 k. And how does this recurrence work? Well, so this is certainly true for all n greater than or equal to 1 and all k greater than or equal to 0. Here, if k is less than 0, you need to interpret Snk as 0. Then this would work even for k equal to 0. And how does this work? Well, this counts all permutations in Sn with k cycles. This counts permutations in Sn where n, so this is Sn, and this is a union of sigma in Sn such that sigma n is equal to n, and the second part counts sigma in Sn where sigma n is not equal to n. If sigma n is equal to n, you can just take sigma and restrict it to the set of integers from 1 to n minus 1, and that will give you a permutation of Sn minus 1. And that permutation will have one cycle less than the original permutation of Sn you started. Here, if you have a permutation of Sn which takes sigma n to something other than n, you look at the cycle that n is involved in and just delete n from that cycle and close it up again. And that will give you a permutation of Sn minus 1. And now you ask, how many ways could I recover my original permutation from these, or rather how many of these permutations of Sn minus 1 do I have from which I could recover my permutation? In how many ways could I recover my permutation in Sn? I'll let you think about it a bit. Basically, you have to choose where n goes, which is what gives you this factor n minus 1 up front. I leave this recurrence, the detailed proof of this recurrence as an exercise for you. It's quite easy. And so using this recurrence, it's easy to compute Stirling numbers, unsigned Stirling numbers of the first kind. We'll just start with sigma 0, 0, the number of permutations of the set, the empty set with 0 cycles. Well, there's only one permutation of the empty set. There's only one bijection from the empty set to the empty set, namely the empty function. And so I would say this is equal to 1. So let's just make a table. N equals 0. We have 1. N equals 1. Well, so if you look at this thing here, we have n equals 0, so here n equals 1, so we will draw arrows like this. So S11 will be 0 times S10 will be 0 times S00, and so here we'll get 0, whereas S11 will be 1 times S00 as per this relation, and so here we'll get 1. Well, maybe I should write down the base case more explicitly. 0k is equal to 0 for k greater than 0. So here, if you want, you can think of all these as 0, but I'll ignore those. I'll just write it as a triangle of numbers rather than an array of numbers. Now here we have 1, 1. So what I'm doing is, Here we have n equals 2. So this multiplying factor is n minus 1. And this is 1. So what we do to compute this is we just take this number multiplied by 1. We take this number multiplied by 1, take this number multiplied by 1, add it, we get 2, 1. So this is for n equals 2. For n equals 3, we'll take vertical arrows 2, 2, 2 and diagonals 1. And now what we get here is, oops, this is still 0. So here we get 0. Here we get 0 times 1 plus 2 times 2. So that is 2. Here we get 2 times 1 plus 2 times sorry, this is here is 1. 0 times 1 plus 1 times 1. So this is 1 times 1 plus 2 times 1, that's 3. And this is 1. So if you're wondering what I'm doing here, I'm just using this recurrence relation to compute the unsigned Stirling numbers of the first kind as n increases. So now the picture I draw is this. Here 0, 6, 2 times 1 is 2 plus 3 times 3 is 2 plus 9, 11. 3 times 1 plus 3 times 1, that's 6, 1. And n equals 5, we get 4, 4, 4. And so you can actually compute these things pretty fast. 6 fours are 24, 44 plus 6 is 50, 11 plus 24 is 35, 4 plus 6 is 10, 1. So this is, for example, this is SN1, S51, S52, S53, S54, S55. This S53 here, for example, is the number of permutations of the set 1 to 5 which have totally 3 cycles. Okay, so this is the triangle of unsigned Stirling numbers of the first kind. You'd seen in the exercises in one of the earlier weeks the Stirling numbers of the second kind. Let me just recall these for you. In case you haven't worked through those exercises. So S and K is just the number of set partitions, number of partitions of the set N with K blocks. And the recurrence relation for this, again, not difficult to show. S and K is S n minus 1, K minus 1 plus K times S n minus 1 K. And the base cases are S and K equals 1. Well, I'll just write using the Kronecker delta. So this Kronecker delta, delta nk, this means that it's equal to 1 if n is equal to k and 0 if n is not equal to k. But this only holds if either n is equal to 0 or k is equal to 0. So what we're saying is that if 1 of n and k is 0, then the only case where s and k is non-zero is when n is 0 and k is 0. In that case, it is 1. Think about why this should hold from the definition. And so similarly, this triangle is also easy to compute. So you start with 1. Now the vertical arrows depend on how far to the right you are. And the diagonal arrows are still 1. So sorry, this is 0. This is 0. you can't have a set partition of an integer greater than 1 with no blocks. So this again becomes 0 here, and this becomes 1. This is again 1. Now 0, 1, 2. These are still 1. And what I get is 0, 1, 3, 1. 0, 1, 6 plus 1, 7, 6, 1. Let me just do one more row up to n equals 5. Zero, 1, 15, 25, 6 plus 4, 10, 1. So this is SN1, SN2, well, 5, 1, S5, 2, S5, 3, S5, 4, S5, 5. And the thing is, we have n factorial is summation k goes from 0 to n Stirling unsigned Stirling numbers of the second kind, of the first kind, because they're totally n factorial permutations of the set 1 to n. And on the other hand, we have Bell numbers for Stirling numbers of the second kind, the total number of permutation set partitions of the set 1 to n. And these two triangles of numbers have very interesting properties, which I'll let you explore partially on the assignments.